Hello, so this is a revision video for AP Chemistry 1.5, Atomic Structure and Electron Configuration. Atoms are the smallest indivisible units of an element and consist of a small, dense, positively charged nucleus containing subatomic particles called protons and neutrons. This nucleus is surrounded by another type of subatomic particle called electrons that are negatively charged. Because the nucleus of an atom is positively charged and the surrounding electrons are negatively charged, there is an electrostatic force of attraction between them. This attraction can be described by something called Coulomb's law, where F is proportional to Q1 times Q2 divided by R squared, with F being the force of attraction, Q1 and Q2 being the charges of the two particles, and R being the distance between them. If we model the nucleus as a positively charged particle, then this equation can be used to describe the attraction between the nucleus of an atom and the electrons that surround it. The smaller the R value, so the closer an electron is to the nucleus, the stronger the force of attraction. Equally, the greater the nuclear charge, so the more positive charge the nucleus has, the stronger the attraction as well. Electrons can exist at different distances from the nucleus of an atom, because they are arranged in energy levels or shells. These are labelled by the principal quantum number n equals 1, n equals 2, n equals 3, and so on. The model of the atom becomes more accurate when we divide each main energy level into sublevels. These are labelled as S, P, D, and F, and they differ in both energy and shape. Not all sublevels are present in each energy level in an atom, and they're sometimes referred to as subshells. The n equals 1 energy level has only an S sublevel. The n equals 2 energy level has an S and a P sublevel. The n equals 3 energy level has an S, a P, and a D sublevel. And the n equals 4 energy level has an S, a P, a D, and an F sublevel. Each sublevel contains one or more atomic orbitals. An orbital is a region of space in an atom where there is a high probability of finding an electron. Each individual orbital can hold up to 2 electrons, a pair, each with opposite spin. Different sublevels contain different numbers and shapes of orbitals. An S sublevel contains only one orbital that is an S orbital. It is spherical in shape and is symmetrical around the nucleus. Because it only has one orbital then, an S sublevel can only hold a maximum of 2 electrons. A P sublevel contains 3 orbitals, which are called p orbitals. They are labelled as px, py, and pz. They are often described as having a dumbbell-like shape, although this isn't strictly speaking true. It's a nice visualization to use at this level. Each p orbital can hold up to 2 electrons, meaning a p sublevel can hold a maximum of 6 electrons. A d sublevel in an atom has 5 orbitals in and can hold a maximum of 10 electrons. The shapes of orbitals in the d and f sublevels are quite complicated, and we don't need to worry about them at this stage of the course. From Coulomb's law, we know the closer an electron is to the nucleus of an atom, the more attraction it has to it, and therefore the lower in energy it is. As a result, electrons fill subshells in order of increasing energy or distance from the nucleus. This is called the Aufbau principle. A 1s subshell is filled before a 2s subshell, a 2p before the 3s, a 3p before the 4s, and a 3d before the 4p. Note that the S subshell in the 4th energy level is actually filled before the D subshell in the 3rd energy level because it's actually slightly lower in energy. Electron configurations show how electrons are arranged within atoms or ions. The notation uses a number for the shell n, a letter for the subshell, so S, P, or D for example, and a superscript for the number of electrons. For example, oxygen has an atomic number of 8 and so has 8 electrons. This would give a configuration of 1s2, 2s2, 2p4. Shorthand notation uses the nearest noble gas to represent inner or core electrons. Core electrons are the inner filled shells within an atom. Valence electrons are in the outermost shell and determine chemical reactivity. For example, oxygen has 2 inner electrons in the first shell and 6 valence electrons in the second, its outermost shell, the 1s2 being core electrons and the 2s2, 2p4 being valence electrons. When atoms become ions, they lose or gain electrons. Cations are positively charged ions that are formed when atoms lose their highest energy electrons. For example, sodium will lose its free s1 electron first to become 1s2, 2s2, 2p6, because the free s1 electron is the highest energy electron in the atom, so takes the least amount of energy to remove. Anions are negatively charged ions that are formed when atoms gain electrons. The gained electrons go into the next available orbital within the atom. For example, when an atom of chlorine gains an electron to become a chloride ion, the extra electron goes into a space in a p orbital in the free p subshell, given a complete configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Transition metals provide an exception to the general rules, and when transition metals form ions, electrons are usually removed from their 4s subshell before their 3d subshell. For example, iron will go from Ar4s2 3d6 to Ar3d6 when it forms an Fe2+ ion. Exam tip here: when writing electron configurations, always double check that you've filled subshells in the correct order and that your total number of electrons matches the element or ion's charge. For ions, always remove electrons from the outermost shell, highest principal energy level, first. Ionization energy is the energy required to remove an electron from an atom or ion. It's based upon the distance the electron is from the nucleus of the atom, the nuclear charge of the atom, and the level of shielding. Electrons further from the nucleus are easier to remove as they have less electrostatic attraction to it. The stronger the nuclear charge of the atom, so the more protons in its nucleus, the stronger the attraction between the electron and nucleus, so the harder it is to remove the electron. The more inner or core electrons there are inside the atom, the weaker the attraction the outer electrons have to the nucleus, making them slightly easier to remove. This is referred to as inner electron shielding. As a general trend, ionization energy increases across a period, so left to right in the periodic table, and decreases down a group, so top to bottom.